Okay, next up we're going to tie in binomial theorem with probability, and this is called binomial probability. Example, so if you toss a coin 3 times, what's the probability that it will come up heads twice and tails once? Okay, I'm going to use my favorite blank method for this problem. So we have 3 different events or tosses. So we have toss 1, toss 2, should be a T, or toss 3. Okay, so we're going to consider each one as a separate event and figure out what the probability of each one is. Okay, so what is the probability that will come up heads twice and tails once? So we're going to call this heads, this event heads, and this event tails. What's the probability that it'll come up heads here? So there's only 2 choices, and we want one of them, so it's 1/2. And heads here is 1/2, and heads here is 1/2. Okay, so the probability of heads is 1/2, the probability of tails is 1/2. We have 3 different tosses. Okay, now this is the more challenging part. There are many ways to do this. You could have heads, heads, tails, like I wrote. You could have tail, heads, heads. You can have heads, tail, heads, and that would be all the ways to do it. So there are actually 3 different ways to make this happen, so we'd want to multiply that by 3. Now in this case, the ways there are to do that was easy to count out here. It won't always be count out, so we want to translate that into something we can calculate. Okay, so that actually comes from there are 3 coin tosses happening total, and we're choosing 2 of them to be heads. This will make more sense in the next example. And then for heads, we want that to happen twice, so it's 1/2 squared. And we want tails to happen once. So this is our heads decision, this is our tails, and this is the number of ways to make that happen. So more specifically, I'm going to call this number of ways to win. In our case, winning is getting heads twice, but again, this will make more sense in the next example, but I just want to show you how this actually connects to binomial theorem. So this is your combination coefficient, and this is your probability to the k, or whatever variable you call that, and then this is n minus k, so 3 minus 2. This is going to make more sense, so let's talk about Jack and his free throw shooting. So he's an 80% free throw shooter. It means he makes it 80% of the time. He shot 7 free throws in the New Trier game, and we want to know what the probability is that he makes exactly 5 of them. So I'm going to set up my blanks again, but you don't have to do this every time once we get good at it. 1, 2, 3, 4, 5. So these are his wins. And then if he wins 5 and he takes 7, he's got to lose 2. Okay, when I say lose, I mean he doesn't make it. So what's the probability of each one? So we'll call this toss 1. This is toss 2. Or throw 3, 4, and 5. And this is the other ones. So in the first one, he has an 80% chance of making it. So you can write this 0.8. You could also write it as 8/10, or even 4/5. Doesn't matter. Okay, pick your favorite form. So in toss 2, he also has an 80% chance. And the 5 that we want him to make, he has an 80% chance. So then the 2 we don't want him to make is a 0.2, because 80% chance of making it means there's a 20% chance of not. Now, just like the last problem, there's more than one way this can happen. So he could make the first 5 and miss the last 2, or, he could even miss the first 2 and make the last 5, or some combination of that. Okay, so there's multiple ways to do this. So we need to multiply by the number of ways there are for this to happen. Now, this would be a lot harder to count than this one up here, which is why using a combination is good. And just to reiterate why this is a combination, it's a combination because order doesn't matter. It doesn't matter if he makes the first 5 and misses the last 2, or the other way around. So that's why it's a combination. In this case, there's a 7 total, and the wins, quote unquote, is what he makes. We want 5 of those. So it's 7 choose 5. And you can rewrite this a little bit more simply. And 7 choose 5, and then it's 0.8 to the 5th power, because we want those 5 wins to happen, and then 0.2 to the 2nd power. Again, you don't have to write out the blanks every time, but I find it's really a lot easier to understand why this makes sense by thinking them as individual events. Okay, so we should probably go ahead and calculate these. So I'm going to have you plug them in your calculator on your own, and I'll come back with the answer. Okay, if done correctly, the coin toss should be 37.5%, and the free throw should be approximately 27.5%. That's rounded. So again, this is binomial probability because you're counting the amount of ways for these things to happen, what the chances are. So this is probability. This is how many ways there are for that to happen.